Okay, in our last video we talked about pH and Ka and pKa and did a little bit of math as a review to try to calculate pH when you have certain concentrations of acids in a aqueous solution. That really leads into this video, which talks about buffers. Um, Buffers are solutions that resist changes in pH, and buffers are super important in biochemistry because all the chemical reactions that occur in your body, or most of the chemical reactions that occur in your body, are catalyzed by enzymes. And enzymes only work at particular pHs. And so enzymes are really picky about the pH at which they're at. And so your body is a buffered solution that resists changes in pH so that the enzymes can work properly. Also in the laboratory, we tend to use buffered solutions because we want our enzyme catalyzed reactions to work. And so we want to keep that pH constant. We don't want it to change when our solution is subjected to external acids or bases. And so buffers resist pH changes, and this video is going to be in general about how buffers do that. So buffers resist changes in pH, and the way they do it is because buffers chemically are a mixture of a weak acid and its conjugate base. So let's look and see how this mixture of a weak acid and its conjugate base is able to resist changes in pH. Okay. So let's look at it. Here's a weak acid over here. We don't really even need to know what that weak acid is. We just know that it has a proton that it's able to donate. When it donates that proton, it generates H plus and A minus, right? And so these are the two components of our buffer. Here's our weak acid, HA. Here's its conjugate base, A minus, right? Since this is a weak acid, we know that this reaction occurs and reaches a particular equilibrium, right? Some of the weak acid dissociates to form H plus and A minus, but not all of it. And there's a back and forth here at equilibrium. So you could imagine making a buffer in the laboratory, right? Let's just get a bottle of acetic acid off the shelf. That's our weak acid, and we weigh some out, dissolve it in water. But then we also need to go find the appropriate conjugate base for acetic acid. That turns out to be acetate. We could get a bottle of sodium acetate off the shelf. We'd weigh out some of that, put it in the same solution and dissolve it, and we'd have a mixture of the weak acid and conjugate base, and we'd have a buffer, right? Here's acetic acid, CH3, as just an example. That's supposed to be a double bond, OH, right? Here's the proton that's going to be donated, and when it donates that proton, it forms its conjugate base, negatively charged acetate. Okay. Now, how do the presence of these two things actually resist changes in pH? How do they buffer? Well, let's insult our buffer with an external source of acid, right? This could be a strong acid that was ingested from the environment, or this could be a result of some metabolic buildup of a carboxylic acid or something like that. But here, let's just say we've got a source of protons, and we're going to subject it to this buffer. Now, how does this buffer react with this H plus? Well, the conjugate base is going to react with this source of acid. And when these two things react together, they form our weak acid, HA. So what we've done is we've taken a strong acid, H plus, we've converted it to a weak acid. The weak acid has much less of an effect on pH than the strong acid would, and that's how the buffer is able to buffer against acids. It does a similar thing if the buffer is subjected to a strong base. Here's a source of hydroxide, maybe from sodium hydroxide. Now this, if you just put sodium hydroxide in water, it really is going to increase pH drastically. But this buffer is going to react with this base, and the acid part of the buffer is going to react with the base, and in a similar fashion, it converts this strong base into the weak conjugate base, which does not have as much of effect on pH. So the way I like to think of buffers is that really I'm putting two types of soldiers into my solution, my acid soldier and my base soldier. When an acid is insulted with my buffer, then my base soldier is going to react with it. It's going to jump on that acid, sacrifice itself, and convert itself into a weak acid. When my buffer is insulted with a strong base, my acid soldiers jump on that and sacrifice themselves and convert that strong base into a weaker base, the conjugate base. Now, obviously, buffers have some capacity to them. You know, if you run out of base soldiers and you add more acid, then you're not going to be able to buffer anymore. And the opposite's true if you run out of acid soldiers. So there's some buffering capacity, which is really defined by the concentration of that weak acid plus the conjugate base in a particular buffer. So let's look at a video that describes this buffer and shows a little animation of what's going on also. So listen to this.
A buffer is an aqueous solution containing both a weak acid and a weak base that are a conjugate acid-base pair. The buffer shown contains the weak acid acetic acid and its conjugate base acetate. These species are dissolved in water. Water molecules are not shown in this animation to draw focus to the buffer components. A buffer solution has the ability to resist changes in pH upon the addition of small amounts of either acid or base. Choose to add a strong acid or a strong base to the buffer by clicking one of the buttons.
Okay, so I'm going to
Only
add
hydrogen ions, H+,
strong acid
from the hydrochloric acid are shown entering the solution. Chloride is not shown because it is a spectator ion. It does not participate in the reaction. The strong acid H+ reacts with the base component of the buffer acetate, CH3COO-, producing the acid component of the buffer acetic acid, CH3COOH. The buffer has resisted a change in pH by removing strong acid H+ from the solution. Only hydroxide ions, OH-, from the strong base sodium hydroxide are shown entering the solution. Sodium ions are not shown because they are spectator ions. They do not participate in the reaction. The strong base hydroxide, OH-, reacts with the acid component of the buffer acetic acid, CH3COOH, producing the base component of the buffer acetate, CH3COO-, and water. This buffer has resisted a change in pH by removing the strong base hydroxide from the solution.